In this video, we want to measure a high-gain frequency-converting LNB. The block diagram looks very similar to our first example on the high-power PA. So we again have some amplifying block in there. But in addition, here included in the device under test, we have a frequency-converting stage. Here is basically a mixer and a free-running LO. The input signal again is provided by a vector signal generator, and the output is fed into the FSWX signal and spectrum analyzer. Again, obviously I could do that as a one-channel measurement, simply comparing on the signal analyzer to what I am expecting the signal generator to transmit. However, the much more accurate measurement results I do get if I compare exactly the outputs of the device under test to the input. Now, why is this example different to the high-power PA example? Simply because we have a frequency-converting device in there, and the two channels of the FSWX receive signals on two different frequencies. Let's go into the block diagram of the FSWX again quickly. We can again see the two signals traveling to the two signal path that is exactly identical as in the previous high-power PA demo. However, what I want to highlight here is the two signal paths have two different and independent LOs. So I can tune the orange signal path to frequency number 1, which is the output frequency, for example, of my device under test. And signal path number 2 can be tuned to a different frequency, representing the input frequency of the device under test. All right, let's go right into the demo. So for the component characterization, we'll use the amplifier measurement personality again. In this case, we have configured it for a dual channel application only. So there is no generator connected. We don't know what the signal or the stimulus is that is going into the device under test. However, we have activated here our reference capture. So we're capturing on both channels, RFA and RFB, at the same time. In terms of measurements, I have configured a gain compression plot here on the upper left-hand side. We have a result summary plot here on the upper right-hand side. And we have a spectrum plot with the output signal in yellow and the input signal in green here. And the most exciting measurement here is on the lower right-hand side, is an absolute group delay measurement on this high-gain frequency-converting device with a fully modulated stimulus. So what do we see? In the gain compression plot, we can see that our device under test is slightly in compression. You can see the right-hand side of the measurement curve bends towards the lower end of the diagram. In the result summary plot, we can get an idea of the EVM, the modulation accuracy that we currently see, which is on the order of 5%. Most importantly, I want to highlight the gain, which is in numbers here 59.3 dB, so close to 60 dB. And we can also see the compression, because the output crest factor is slightly lower than the input crest factor. Most excitingly is this group delay measurement that characterizes the absolute group delay between the input and the output of this high-gain frequency-converting device. So what we see here is a group delay on the order of 5 nanoseconds. It's not constant over the entire channel. It varies slightly, which is expected. However, what we see is it is around 5 nanoseconds, which is roughly the average group delay of this device under test. And again, I want to highlight that this device is a frequency converting device. So our RFB input channel is configured to a frequency of 11 GHz, whereas the output is configured to a frequency of 1 GHz. So at the same time, I can measure nonlinearities, modulation accuracy, and even absolute group delay on a fully modulated signal by using the dual channel architecture of the FSWX. As you have seen, we can measure absolute group delay, modulation accuracy, and nonlinearity in a single measurement. Using the dual-channel architecture of the FSWX, the instrument doesn't even require a repetitive signal or any knowledge of the stimulus. So it can be run on a live DOT outside the lab.